Hello everybody, this is our review of Unit 3, Work and Energy. This is one of my favorite units because it makes a lot of the calculations that we made in kinematics way easier. So let's first start with the definition of work. Work is defined as the line integral of force with the path an object takes. So if it's traveling this way, any force that is parallel to it will add energy to that object. But if it is if it is perpendicular to the object's motion, it will not add any energy. This is also written sometimes as the magnitude of the force in the parallel direction of the travel times the distance it's applied. Oops, the shadow back over there. Or sometimes written very simply as F dot D. Be very careful with how you use F dot D. This is the pure mathematical version. Sometimes it is simplified to this, but you should always be careful because if you have something like a spring, like the work a spring does, you will write F spring dot ds. And if you wrote that out even more, you would actually get negative kx dot dx, dx. And this would not be the same as simply writing negative kx times x. They're not the same. So be careful when you are defining your work. Next, let's work on identifying the system. Let's take a large planet and a ball very high up, of course, but a ball nonetheless, and another ball. And now let's consider when we only consider this to be our system, and when we consider both the ball and the planet to be our system. So if these are both a height h, let's consider how we can solve for the final kinetic energy. And let's assume that we drop these from rest. So first let's do where we consider Earth to be an external body. So there's now an external force, Fg, which means that in our work equation, we can write Fg dot h. Now again, these are in the same direction, so we can write it this simply, which would mean work is equal to mgh delta k plus delta u. But before we resolve what delta u is in this case, let's look at the other one. Are there any external forces? No. The force of gravity is internal to our system, which means that there are no external forces, so our work external is going to equal 0. Because our work external is also equal to our delta k plus delta u, this is 0, which means that our delta k is going to equal negative delta u. This is a very useful expression, but let's see if it's the same over here. Delta u has to be equal to 0 here. Why? We are not considering potential energy. We would if we were considering Earth to be part of the same system, but because they're not part of the same system, we are not considering potential energy. So we're going to write that as 0. And we have that delta k equals mgh, and our kf is mgh because our k initial was 0, because it started at rest. Now here, delta k is going to equal u initial minus u final because of this negative sign in the front. And because u of gravity is given as mgh, we're also going to find that kf equals mgh. Now, what's extremely important to realize is that we had very simple initial conditions. Everything was at rest. We ended at a 0 potential. We have to remember that sometimes these balls can be thrown down with an initial speed, or not even just balls, but any object can have initial velocity or initial kinetic energy or an initial potential energy, and you have to consider that. Another thing is that 0 potential is arbitrary. It is in reference. So for these problems, we considered that our potential energy was at the surface of Earth, where we called u equals 0. In both of these. Oh wait, no, sorry, not for this case. For this case. we considered that our potential energy was at the surface of the Earth being 0. You always need to define your 0 point of potential, your 0 potential point. Next, let's apply this to a problem with a compressed spring. You may see this in an FRQ, where you will see a block with an initial speed, v0, on a hill with a height h, and a spring with a spring constant k. And your job is to find the distance d, which is the maximum compression of the spring when the block fully slides into it. Now, for the sake of this question, let's refer to the bottom as u equals 0. Let's consider that gravity is acting down, that this direction is our positive x direction. But because we are looking at it in terms of energy, we do not need to worry about velocity components or even necessarily what direction is positive and negative, because we are looking at energy, which is a scalar quantity. So let's consider this to be a three-body system. The block, the Earth, and our spring. If we did not include spring here, we would have to do an integral with the force of the spring with respect to the displacement of the block. But because that is outside of the scope of our discussion, we will only be looking at it as a three-body system. So the work external is 0 because there are no external forces. So the change in our kinetic energy must equal negative the change in our potential energy. Let's also remind ourselves that the spring is going to start out uncompressed. So we're going to have delta K equals negative delta U of the spring minus delta U of gravity. So again, writing this out again, delta U of the spring is going to equal negative delta U gravity minus delta K. I'm sorry, I forgot to write the U. It's a little unfortunate. Okay. So we're going to have U spring final minus U spring initial is going to equal U gravity initial minus U gravity final minus the kinetic energy final plus the kinetic energy initial. The kinetic energy final is going to be 0 because it's going to be at rest when it stops, when it's fully compressed. The U gravity final is going to be 0 because it's going to be at our 0 potential that we defined earlier. And our initial spring energy is going to be 0 because it is uncompressed. So let's write this out. USF equals UIG plus KI. Okay, finally, ready to solve. Equals mgh plus 1/2 v naught squared. Okay, so we can write this again as x squared equals 2m over k gh plus 1/2 v naught squared. And we can get that our displacement, which we can actually just write as d because that's what the question is asking for, of the spring when fully compressed is going to be the square root of this quantity. And in terms of actual calculation, it was very short. I don't know if you remember how we did our kinematics problems, but the calculations were definitely longer and honestly more annoying. Energy methods are my preference. If you like the kinematics approach, you're always welcome to do that. In fact, most of the questions on the AP test will allow you that degree of freedom. And I hope you are able to use this as a tool and to understand why we use different methods of defining a system and how it can play out in our calculations. So good luck, and I hope this